Hello and welcome to the week 5 for the materials and selection design. And as you remember that this week is going to be the quiz week. So this lecture is going to be the only face-to-face meeting we're going to have this week. So we start with the topic for this week, which is going to be design considerations, which is about the main important things, which is the failure mechanisms. So once again, you can see the example that we put here is the ocean gate. Okay, sorry for that. Anyway, the material failure during the service is nearly always undesirable because this can cause a harm to people or animals and leads for the damage of the property, disturbance of the supply chain and the related system, and generally cause expenses. While the cause of the failure can be predicted, it is difficult to predict when failure will occur. Hence, a consideration of the failure is a critical step in the design process and incorporates with the material selection among the other considerations. Topic of the metal failure is very large, but it will be introduced in this topic. We commence with a fracture. So the fracture fundamentals. I think that you saw this stuff around us every time, like the crank can be fractured, the bottles can be fractured, depending on the material we're going to have. So the fracture definition is a simple fracture is the separation of a body into two or more pieces in response to an imposed stress at a temperature that is going to be low relative to the material melting temperature. The fracture can also occur due to the fatigue, where the applied stress is going to be cyclic, or the creep, where the time dependent, usually at elevated temperatures. The applied stress can be tensile, compressive, torsional, or shear, but only tensile will be considered in this introduction. The two fracture modes prevail are the ductile and the brittle. Determining which mode is likely to occur is going to be based upon the concentrations of the material to deform the plastically, which is going to be mainly absorb the energy. Metals typically accept a ductile fracture, while the ceramics will accept the brittle fracture. It is also important to know that the fracture modes is relative and can vary according to the strain rate or the temperature. Fracture also results from the distinct processes like the crack initiation, which is how does the crack form, and the crack propagation, which is how does the crack grow, specifically about the speed of the growing. So the crack propagation is the cracks already has been done, but it's going to be how it's going to be increased and how it's going to be grow and what will be the speed of this growing. So from the standpoint of the design and the safety, ductile fracture preferable to the brittle fracture. Now, I would like you to actually research and answer why it's going to be more preferable than the brittle fracture. So we start with the ductile fracture. It is the mode of the mechanical failure occurring in a material that can plastically deform. Examples include the soft metals like the gold or the lead. It can also be observed in the glasses at sufficiently high temperatures. The key characteristics of the ductile fracture is the appearance of the nicking. The nicking is a process where the cross-section of the material reduces under the action of the applied load, and eventually is going to be crack will form, leading to the fracture of the article. A result of the nicking is the cup and the cone fracture, where the two pieces of the article can be fit snugly together. So we can have these two examples. You can see that in the case of the nicking, what we're going to have in ductile, if I'm going to put the parts together, this head will be fit on the other head. That's why we call it the cup and the cone shape. Now, the process of the nicking involved a few steps. First, under the application of the load, the material will experience a strain in the direction of the load. And this load to be the beginning of the reduction of the cross-section area of the article. At the center of the neck, the small cavities begin to form, which we call the microvoids. As the nicking continues, the cavities will begin to join to form the crack, which can be the stage of the crack initiations, with the rough elliptical shape. The long axis is going to be aligned perpendicularly to the applied stress, and the crack growth propagation to the procedure to the perpendicular to the load direction also. So we're talking about the first step where that's the load has been added. We're going to start to have some the micro voids inside, and these microvoids are going to be connected together to make the cavities to join together to form the crack, the crack initiation with the crack elliptical shapes. The long axis is going to be aligned perpendicular to the applied stress, and the crack growth, which is the propagation, is going to be proceed perpendicular to the load direction also. Ultimately, the fracture occurs when the crack reaches the surface of the article and rapidly propagates around the circumference. That's what we have in the shape D. Finally, in shape E, we're going to have the crack to be disconnecting the two parts. We're going to have the fibrosis going to be created, and the shear will finish the job. So visually, the interior of the ductile fracture surface is going to be a fibrous in the appearance, and this is going to be an indicative of the plastic deformation that has taken place and the formation of the microvoids. Now this is a closer look about the thing. You can see that the crack will be appeared, and you can see the shape of the particles. So you can see the fibrous actually is going to be very, very clear in the last stage on both ends. Now we're going to the brittle fracture, which is going to be a little bit different from the previous one. Brittle fracture occurs without plastic deformation, so it's going to be happen suddenly. That's why you can see that the shape here is not going to be longitudinal. It's going to be just a flat surface which has been broken. So it's also proceed rapidly due to the inability of the materials to absorb the energy. The direction of the crack propagation is going to be highly perpendicular to the axis of the applied force and tends to yield a flat fracture surface. The brittle fracture demonstrates several distinct appearances, like for example, in the presence of the V shape, which we call the chevron, marking that it points toward the location of the crack initiation. And this is typical in some steels and can be observed with the naked eyes. We can also have the appearance to be lines or ridges, and that actually going to be radiated out of the crack initiation site and can be observed with the naked eyes as well. In hard and fine-grained materials like the ceramic, the fracture pattern can be invisible. Finally, the amorphous materials like the glass, the fracture surfaces appears to be smooth and glossy. So the crack propagation during the brittle fracture takes place in two modes. The first one is going to be the transgranular fractures, where upon the initiation, the crack will propagate via the specific crystallographic planes, which we call the cleavages, and passing it through the individual grains. This tends to leave to hide the fracture faces the fracture surfaces, what we call this sprackling. The other mode is going to be the intergranular fracture, where upon the initiation, the crack propagates along the grain boundaries, yielding a 3D fracture surface. So the occurrence of other moods is going to be determined by the strength of the grain boundaries, which can be weakened in the number of ways. So the principles of the fracture mechanics. Ductile materials can failure by a brittle fracture under the certain circumstances. The consequences is going to be a catastrophic failure that may have given a little or no warning. The need for the predictable assessment of the failure has led to the developments of the fracture mechanics as in the engineering specifications. So the fracture mechanics consider the several variables relating to the given loading and the failure scenario. Central to the approach is going to be the concept of first the stress concentration and the second is going to be the fracture toughness. The determination of either the critical stress sigma c or the critical flow size the sigma the AC, which will yield rapid fracture if exceeded. So the stress concentration is a very important point. So whilst the body may be acted upon and applied load, like the normal stress sigma O, the presence of the surface or the internal flows can result in a localized region where the stress has been actually magnified or concentrated. In this case of the crack tip is going to be the location of the magnified stresses sigma m is going to be appeared. So to calculate the magnitude of magnified stress, we can use the equation that the sigma m is going to be equal to sigma o multiplied by the ratio of the a to the rho t up to power 0.5, where the sigma m is the maximum stress, sigma o is the nominal stress of the material, which is a property of the material, the a is going to be depth of the surface crack or the half radius of the internal crack, and the rho t is going to be radius of the crack tip. The stress concentration also has the effects is going to be more serious in brittle materials due to the ability of the ductile material to plastically deform under the action of the sigma m. We know that the sigma m definitely is going to be more than the sigma y, which is the yield stress, if you remember it. In ductile materials, the deformation and the crack is going to be serves to slow the crack propagation or stop it altogether until the applied loads is going to be increased further. However, in the brittle materials, the yielding doesn't occur, so cracks propagation will be proceeded rapidly. Under this assumption, a critical stresses, or sigma c, can be approximated by the equation of the sigma c is equal to 2 multiplied by the nominal stress multiplied by the ratio of the 2 multiplied by the elastic modulus multiplied by the specific surface energy divided by the pi multiplied by the depth of the surface crack, all taken to the power of half. The fracture toughness. The critical stress concept has been expanded, leading to the concept of the fracture toughness or the Kc. The Kc is a measure of the material resistance to the brittle fracture when the crack is present. And the Kc can be calculated by the equation of the y, which is the parameter relating to the crack dimension to the overall body geometry, which often going to be between the range of 0.95 to 1. Multiplied by the sigma c, which is the critical stress that we calculated from the previous equation, multiplied by the pi a under square root. The crack surface displacement can proceed via three modes. First one is tensile modes or the plane strain. We can have the second mode is going to be the sliding mode, and the third one is going to be the tearing mode. The measured fracture toughness will indicate the relevant mode as per the KLC for the mode I. So the fracture toughness for different materials can be shown in this table. We have it for the materials like the ductile materials like the aluminum alloys and the titanium alloy and the alloy steel. And we can have for the ceramics like the concrete, the soda lime glass, and the aluminum oxide. And we can have it also for the polymers. We can see that the range of the yield strength is going to be varied between the metals, ceramics, and the polymers, where in the case of the ceramic, they are purely brittle materials, so they don't have any yield stress. They can do a fracture at this point directly. So the value for the KIC will be changed according to that. We can see that the highest value for the KIC is going to be in the case of the metals, and this will drop down dramatically in the case of the ceramics, and it's going to be a little bit higher in the case of the polymers. So the KIC is sensitive to many variables, including first the strain rate, the temperature, the grain size, and the material processing artifacts that's impacted the sigma Y. So you can see that different materials definitely is going to have a different value for the KIC. You remember the strain rate, you know the effects of the temperature, you know the effects of the grain size, and also what is the method that the material has been processed with. So as an alternative to the critical stress, a critical flow size can be determined using the equation of the AC is equal to 1 over pi multiplied by the square power of double 2 power of the KLC divided by the sigma Y. Now you can see that this equation actually is the rearrangement of the previous equation. So again, the AC is the critical flow size, the sigma is the applied stress, the Y is the parameter relating to the crack dimension to overall body geometry, and the KLC is the fracture toughness in the mood 1. From this acceptable level of the flow size can be determined accounting for the variable flow detection options. The word fatigue before, but not maybe in the mechanical engineering. So the fatigue is a form of the failure that occurs due to the application of the dynamic and the fluctuating stresses. Example will include the stresses subjected to an aircraft due to the takeoff and the landing. So now you can see that the fatigue and the fracture. So the fracture was a constant load to be added. If I'm going to have this load to be fluctuating, this will be a fatigue. The result of the fatigue is going to be a brittle-like failure that occurs at much lower stress level than expected. The failure is also going to be very rapid and often going to be catastrophic. A critical element of the fatigue failure is a time. So due to the accumulative effects of the cyclic stresses and strain. The fatigue is very common failure mode for the metals, but also occurs in polymers and ceramic, but not the glasses. So you can see here in the figure 8.18 the variation of the stresses with the time that account for the fatigue failure. So in the diagram A, you can see the reverse cycle, a stress cycle in which the stress alternates from the maximum tensile stresses or the positive value to the maximum compressive stresses, which is going to be a negative value, in which the maximum and the minimum value is going to be changing the values alternatively, maximum to minimum. So always going to be positive, negative value stresses on the part. In the figure B is the repeated stresses cycle in which the maximum and the minimum stresses are going to be symmetrical relative to the zero stress level. And the mean stress value, sigma m, is going to be a range stress of the R, and the stress amplitude of the sigma a are going to be indicated. So the mean stress is not going to be zero, it's going to be above or sometimes lower than the zero. In the figure C, you can see the random stress cycle, which is going to be the most dangerous one. So we can represent the SN curve, and actually materials can be assessed for its fatigue behavior by subjecting it to a program of the cycle stress. For axial loading, the test configuration as per the below can be used to indicate or to induce the oscillating tensile and the compressive stress in each side of the sample as it is going to rotate it at specific speed. So if you're going to analyze this figure, you can see that this is my specimen, which once again is going to look like the dog bone. This have a certain initial diameters, is going to be subjected to a load on both sides. The motor will cause the specimen to rotate. It's going to have a cyclic loading, so not going to be on one direction like what we have in the bending test, and this will cause the material to fail at a certain stage. Taking these results, and we can simply sketch the diagram we have here, the cycle to failure, the number of the cycles against the maximum stress has been applied in megapascal. So you can see here that the test has been done for different materials, and you can see that the range of the cycles of the failure starting from the 10,000 up to 10 up to 0.9 for the case of the aluminum alloy. So under the applications of the given stress amplitude, the sigma A, the number of the rotation until the failures are going to be counted. So through the A series of the tests at the different applied stresses, the SN curve can be generated as we see here. So from there you can tell that the better material to take the high stress is going to be the titanium alloy. I know it lasts for something like 10 up to 5 times 10 up to power 7 cycle, okay, but it's going to be performing much better than the case of the T6 aluminum alloy that can be last to something like 7 times 10 up to power 8 cycles, but it's going to be with something like 120 megapascal stress rather than the titanium, which is going to be felt at the 490 megapascal stress. So from this curve, the number of the cycles at the given sigma A are predicted. So when I say predicted, you can actually set what the number of the expected cycle and what the stress you are going to achieve for this amount. So once again, generally the higher the stress amplitude is, the fewer cycle until failure is going to be appear, and vice versa. However, there are two distinct SN behavior, which are first, for some materials, the number of the cycles approaches horizontal, indicating a fatigue limit, and other materials demonstrate the declining end value and indicative of an eventual failure at any cyclic load. From these fatigue strength or the fatigue life are going to be used to define the specific number of the cycles at a given stress amplitude. Usually fatigue is going to be related to a crack initiation and the propagation. So you can see here once again some of the examples which are going to indicate to us the fatigue zone and the final failure. So that will be the origin point of the beginning of the work, and then we're going to have the failure zone, it's going to have the fracture or the final failure is going to be appeared. So the process of the fatigue failure demonstrates three distinct steps, which are going to be first the crack initiation, which usually at the component surfaces where the stress is going to be concentrated, specifically scratch, the fillet, the thread, or the dents and extra. The crack propagation, where under the action of each stress cycle, the crack will incrementally grow. And finally, the final failure will occur rapidly once the crack reaches the critical length. The factors that affect the fatigue life are: the fatigue life or the materials components are influenced by many factors, such as the first one is going to be the mean stress. And we saw that. The higher the mean stress is, the less number of the cycles going to be achieved. Or from the SN behavior, reducing the mean stress will lead to the increase of the fatigue life and vice versa. The surface effect, where the surface often going to be provide a size of the stress concentrations, and this may be designed or from the surface treatment, like example the machining, or the introduction of the residual compressive stresses at the surfaces, like what we have in the shoot peeing process, is going to be beneficial for the fatigue life. Usually, I can tell you that the best surface finishing, the best fatigue resistance. Finally, we have the environmental effect, where thermal cycling can induce the thermal stresses that reduce the fatigue life. And corrosive environments can lead to the small bit formation on the materials, hence providing stress concentration sites and decrease the fatigue life. Now, another term that you'll learn about is creep. I may demonstrate that for you in the class last time. So the creep is a deformation process that occurs when the material is subjected to a constant load at an elevated temperature. The creep ultimately will lead to the material to rupture, but the failure of the components can occur beforehand due to the permanent dimensional change that results. The example of the applications where the creep must be designed are going to be turbine rotors in the jet engine. The creep behavior is complicated, but the generalized form can be described. We first have the initial loading, where the components undergoes an elastic deformation upon the initial application of the stress, and that's provided it doesn't exceed the yield stress. This initial deformation is not a creep, as the material will recover if the stress will be removed. The second stage is going to be the primary transient creep. So after initial loading, the material continues to strain, but the rate of the strain decreases with the time. And this is due to the effects of the strain hardening. The secondary stage, which is steady state creep, the creep rate will become constant and trends to persist for a long duration. We have the territory creep, where the final stage that displays a sudden increase in the creep rate, ending with the component failure, which is going to be the rupture process. So when designing for the creep, the secondary or the steady state creep behavior is usually going to be the most important consideration for us. So you can see here the creep behavior, like the strain value or the creep strain value according to the time. We're going to have the primary, secondary, and the tertiary. So usually we're going to focus on the secondary stage of the work. You can see also that the creep is going to be an effects with the temperature. The temperature can make the value of the creep to be higher. Also, we can have the influence of the stress. That one is going to be time with deep strain, creep strain, by having the equation for the sigma against the time. T is the time, and the sigma is the stress we are going to apply. So the effects of the temperature, the extent of the creep demonstrated by the material will generally going to increase with the increased temperature or the increase with the increased stress. So both will manifest as going to be increased deformation at each creep stage and a reduced duration for each stage. For the metals, creep is going to be an important when the temperature exceeded 40% of the melting temperature. In some cases, it is practical to experimentally determine the creep behavior of the materials or the components under the realistic scenario. However, in many cases, the duration involved can be too long. For example, it's going to be 4 years. Fortunately, it is possible to reduce the long-term creep behavior from the short-term creep behavior that is going to be accelerated by the application of the higher stress or the higher temperatures that can service this scenario. So the strain rate dependency on the stress, where the strain value is going to be equal to K1 multiplied by the sigma n. Well, the sigma n mainly is going to be the stress we're going to have, sigma up to power n, sorry. Stress is going to be the sigma in the end is going to be the material constant. The K1 is also a material constant. The strain rate dependency on the stress and the temperature can be calculated from the second equation. Well, here we're going to have the exponential of the QC divided by the RT, where the QC is going to be activation energy for the creep, and the R is going to be the ideal gas constant, and the T is temperature in Kelvin. So in the high temperature alloys, a creep resistance in the material is going to be favored by first the high melting temperature, the high realistic modulus, and the larger grain size. Finally, the processing techniques to an engineering specific microstructure. Finally, the module summary is that under the signal loadings of relatively short duration, the material fracture can occur via the ductile or the brittle fracture. The second point is that when the applied load is going to be cyclically, the mechanical failure can occur in a brittle fashion, which is going to be called the fatigue failure. The third point is when the single load is going to be applied for long duration at a sufficiently high temperature, the creep will occur loading to a brittle failure. Finally, the fracture, the fatigue, and the creep failures mechanism can be predicted. Once again, the important reading for this topic is going to be the chapter 8 of the Callister and Redwich for the material science and engineering 10th edition. Okay, thank you for your listening, and we are going to have more questions from you in the class.